everyone. We are very happy to have Mallesh here coming from UPenn talking about private equilibrium and no regret learning. And just a quick reminder that from 3 p.m. to 5 p.m. we're going to have a tutorial of what is it? Mean field equilibrium and applications that Ramesh will have from Stanford. So take it away.
Thank you for this is joint work with Michael Kearns, Aaron Roth, and John Ullman. For those of you who are economists in the audience, those are at least 2 out of 3 of them are reasonably famous. John Ullman is an up-and-coming grad student. For those of you who are computer scientists, I'm the person you don't know. I'm an economist at UPenn. All right. All right. What's this paper about? So, if you're in this talk, you've sort of heard at least one other talk on standard mechanism design, and the general question that gets asked is, we want to achieve some outcome. People have private information that is relevant to deciding what the right outcome is. Can we give people incentives to accomplish, to sort of get them to reveal their private information so that then we can get the right outcome? In this paper, we're going to add a twist to this old story. And what's that old twist? The agents are additionally worried about the privacy of their private information. So it's not just that they have something that's payoff relevant, they also don't want other people to learn it. As in what proceeds in this talk, I'm just going to take this as a given. I'm going to be agnostic about why they don't want it revealed. But if you want motivations for why, think about, for instance, either that the underlying private information is sensitive for some reason, for example, healthcare, or think about a story where there is some unmodeled future interaction and they're worried about strategic concerns in this future interaction, so they don't want their information revealed today. Either which way, I'm just going to take this as a given that they're concerned about the privacy of their private information. If you don't care about privacy, here's an alternate way to think about the exercise. You can think of privacy and the analysis that we're going to do as just a tool that we're going to use. And what we're going to be concerned with is a variant on a standard mechanism design problem. In a standard mechanism design setting, the mechanism is, after an individual rationality constraint or something like that, we give the mechanism the power to enforce outcomes. So once everyone's revealed their private information, the mechanism can force each person to do what the mechanism tells you to do. Here we're going to study what we call a recommender mechanism, or what has been called a recommender mechanism. So what I mean is that agents need to be incentivized to follow the recommendations of the mechanism. All right. If you're, here's sort of an illustrative example. I don't want to say motivating, but it should explain the enterprise that we're trying to get into. Think about GPS-assisted navigation. So each of you have phones. You know where you want to go. You enter it into your phone. Your phone looks up directions. And currently what your phone is doing is it's sort of getting data about what the traffic on all possible routes to your direction is and giving you some best route given the current traffic. Let's think about a hypothetical world in which everyone used one navigation service. So everyone has coordinated on Google Maps, Apple Maps having ruled themselves out of consideration. Now, of course, this service is going to produce all the traffic. Everyone is going to enter their directions into Google Maps. Everyone is therefore going to get directed by Google Maps, so all the traffic, all the congestion is being caused by how Google decides to route various people. Implicitly, what's the constraints that a designer for Google Maps should consider when he designs his system? I posit that there are 3 concerns. The first is that Google Maps is just a recommendation. It can't force you, until Google comes up with self-driving cars, it can't force you to follow the route Google is telling you to take. So it should be giving you the fastest route to your stated destination, given the congestion caused by the routes it gave to everyone else. Otherwise, you wouldn't follow the directions that are given. In short, it should be computing an equilibrium of the game given once everyone is told Google where you want to go, or where they want to go. The second is a standard consideration from mechanism design, incentives. we would want that each person should be incentivized to truthfully report their direction, their destination, sorry, and then get directions to that destination rather than giving some incorrect destination, getting Google to compute an equilibrium of the wrong game, and then following some other route which might be better because you've moved all the traffic away somewhere else with regards to your true destination. And the third constraint is privacy. Privacy basically says that I wouldn't, based on the routes you get, I don't want you to be able to tell where I'm going or what my destination is. So I would not like that you know based on your routes whether I decided to come into work today or went off to watch a baseball game down in Wrigleyville. All right? So formally, our analysis is going to be about the design of mechanisms that can do all these three things.
So privacy could be very, very strict.
Yes.
If you obviously you get no information about the entire aggregate.
Absolutely.
So
That's going to be a trade-off, and it's on the next slide. If you, again, like I said, you can do it. We are sort of agnostic which way you go with this. You can think of it as just a design of a mechanism that satisfies the first two, and privacy is the tool we are using to put it all together. Or you can take this constraint seriously, in which case it's a trade-off. Okay. And here's roughly speaking what this paper is going to be about. We're going to take any n-player k-action game. So each player has some k actions. There are n players. Each of these players has private types. That is, in the big n by k matrix, they know their entries in the they know their payoff entries in this game matrix privately. All right. For instance, in the congestion game, I know what my direction. I know what my destination is, and therefore I know what. What my payoff would be given different routes that you gave me. What am I going to give you over the course of this talk? I'm going to construct a computationally tractable mechanism. The input is going to be a report of types, one for each player. The output is going to be a recommended action to each player, such that I have the following three properties of this mechanism. One, the actions that I give everyone will constitute an approximate correlated equilibrium of the induced complete information game. So I will be giving you given everyone's reports, that induces a complete information game. The actions that they're giving are required to be a correlated equilibrium. This, of course, satisfies the obedience constraint that I wrote down a minute ago. I'm going to write down a notion of privacy in a slide or two, or four, and the mechanism is going to satisfy this demanding notion of privacy. And finally, there'll be incentives. Reporting truthfully and following the suggested recommendation of the mechanism is going to constitute an approximate ex post Nash equilibrium. Three uses of the word approximate. All these three approximations are going to vanish as the game grows large, in a sense that we will define formally. Yeah?
So why correlated in the first bullet point and Nash in the third?
Okay, so the Nash is, ex post Nash is because I need something weaker than a Nash equilibrium of the underlying game, complete information game. But following the recommendation is going to be a best response, right? That is the case also in a correlated information. So here I can get the stronger result. Here, except for without additional assumptions on the classes of games we are considering, I can't get Nash. I can only get correlated. Right? So this is going to be the enterprise. These are the results I'm going to tell you. The final result is going to be of the flavor of these results being typed. So no other mechanism can give a more exact equilibrium for a given level of privacy.
So is that saying that the computational tractable part didn't have any bite? So because at the end you said no other mechanism.
That is correct. So the computationally tractable part is just a bonus, that it can be done computationally tractably. No other mechanism could do better any which way. There was another question.
And the tightness is only in the limit.
Sorry?
The
The tightness is an order result, so you can't have any other mechanism that does better. All right? Does a better rate. I'll give you formal definitions in a slide or two. And in terms of contributions, beyond the result, we're going to claim at least two. One, we're going to claim that we have this cool sort of in the computer science literature, there's been this notion of differential privacy, which is how can we guarantee that an algorithm privately computes a summary statistic from a database. We're going to generalize it for these interactive or game settings, and we're going to give a sort of related notion that's joint differential privacy, and we believe this is sort of useful. In particular, we have a positive result with this demanding notion. Secondly, our mechanism design setting is one where there's no transferable utility and no enforcement, right? So the fact that we have positive results here is kind of surprising because normally our mechanism design results are in transferable utility settings where we're going to use payments to support the outcome that we want. Here we can't do that. So we're working with a tougher setting. Any which way, that's the blah blah. Here's the setting. So for the purposes of this talk, n agents, k actions each. Each agent has a private type. I'm not going to define. The type space can be arbitrarily large. All I'm going to ask is that your type is a independent draw from a distribution, independent of everyone else's draw. So in particular, just given your type, you don't learn anything about anyone else's type. All right? Your payoff depends on your action, everyone else's action, and your own type. So this is a private type setting. We normalize values to be in, we normalize payoffs to be in 0, 1. We're going to say that payoffs are gamma sensitive if whenever some agent J changes his action, some other agent J changes his action, regardless of everything else, your payoff can be affected by at most gamma. All right, so this is a assumption that is just buying you some byte. Nobody else is particularly payoff influential on your own utility. Of course, your own action can influence your own payoffs a lot. It's just that other people can't influence, any one other person can't influence your payoff by very much in deciding his action. And our positive results are going to be for the case when gamma is of the order of 1 over n. All right, so for instance, think about large random anonymous matching games. There's some stage game that 2 people play, and the population is just randomly paired off. Now, of course, any one other person's action only has a 1 over n probability of ever interacting with you. So any one person changing his action does not change your expected payoff by very much. Okay. This is going to be our setting. A mechanism, like I said before, is really just an algorithm that takes as input each player's report of type and then spits back out a recommended action to each player from their k actions. Each player only sees his recommended actions, and the mechanism, of course, gets to correlate the recommended action to each player insofar as it likes. Yeah.
So let's think about the sensitivity assumption in the congestion game.
Yes.
So would you argue for it there?
Okay, so in the congestion game, it's a little weird because I'm pushing up the number of people. So you'd think congestion is just going up as a whole. And the 1 over n is really artifact of the normalization to 0, 1. All right, so it's a little tricky what the correct orders mean, but for instance, for random matching, it's very clear what the correct order means. All right. So this is my setting. And now before I go forward, if everyone understands everything, I want to just take 2 minutes to introduce privacy. All right. So here's a worst case notion from differential privacy is a worst case notion from theoretical computer science. It's been all the rage in some parts lately. The question is of the order, you have some database, you want to spit out some, you want an algorithm to process this database and give back some summary statistic. And the question is, how much can a person learn about the individual entries in the database from the statistic that you throw out? We say that an algorithm that takes as input some database D or some space of databases D and spits out something possibly a randomized algorithm in a range space R is differentially private if given any two databases D and D prime, which change only one element, the probability that the algorithm gives a result in an event space S is close to, under the result of the algorithm when it processes database D and the result of the algorithm when it processes D prime, the distribution over the range space R is very similar, regardless of the two databases. All right. So formally, what does this mean? I take, if for instance, I take the salaries of everyone in this room and tell you I'm putting it into a private database, differential privacy would suggest that returning the, letting an algorithm compute the average salary, this is not differentially private. Why? Because the average salary is one number for one database, and if you change, for instance, Jim's salary, that will change what the outcome is. On the other hand, if I take the mean and add appropriate noise, I can create a noisy, I can throw back, the algorithm can create a noisy mean that is indeed differentially private per this definition. Okay? So this is a worst case notion. It has several nice properties in the sense that it isn't so bad that you can't do anything privately. There are possible, you can do all sorts of stuff, plus it composes nicely. So for instance, if I process a given database twice with two differentially private algorithms, then the net result, if I see both the output of both mechanisms, the joint space is also differentially private, of course, less private, but it doesn't completely vanish. It degrades nicely. Okay. So this is the notion of differential privacy that we're going to use. In particular, we're going to modify it to joint differential privacy. And we're going to say that a mechanism is jointly differentially private if, for any player, if you change any player's type.
I'm sorry.
Yeah, sorry.
Let me ask a stupid question.
No.
Suppose that my algorithm just says, whatever you tell me, I'm just going to randomize over.
Yes, that is a differentially private algorithm.
But it's not useful.
It's not useful. I didn't. I mean, differential privacy you should view as a constraint. And I'm going to ask what is the best I can do subject to the constraint. But yes, throwing out noise always is differentially private. It's just not an interesting algorithm. But thank you. So the trade-off intuitively is always going to be how much can I do while retaining this notion of privacy. All right. Now you can ask the same. Now you can ask, what does it mean to be jointly differentially private? It's a simple variant. The idea is that when I submit my type, changes two things. It changes my report, and it changes the joint it changes my recommended action, and it changes the joint distribution of recommended actions to everyone else in our mechanism setting. Suppose I'm willing to trust the mechanism, but I don't trust everyone else. All right? So people don't get to see the action that is recommended to me. Of course, everyone else could collude and see what each of them, the recommended action that each of them got. What I'm asking for for joint differential privacy is that for any person, the recommended actions everyone else is getting are differentially private in that person's type. All right, so if you think of it as all of us using GPS navigation, even if all of you pooled your particular, the routes that you got from Google and pooled among each other what destination you had asked for, you still wouldn't be able to figure out whether I went to school or went to the Cubs game. Right? This is extremely taxing, of course, because it's allowing for arbitrary collusion among everyone else. I don't mind that because I'm going to get a strongly positive result anyway. Yeah.
You get a better trade-off in privacy and utility. You don't have such a strong. I mean, it just seems like a discord between strong privacy but a weak solution concept.
Okay, so why don't I tell you a little bit about how our proof is going to be put together, and then you'll see why it's going to be hard to do anything else, work with any other notion. All right? Are there any further questions about the setting? All right. So that's the question we've sort of given ourselves. Let me tell you the main banner result. The banner result says the following. Given for any game, given the number of players, the number of actions, the sensitivity of the game, the degree of privacy you desire, these epsilons and deltas over here, we can construct a mechanism that is private up to the desired degree and returns an alpha approximate correlated equilibrium of the complete information game for every report of types of the players, where alpha is this. All right? It takes in the sensitivity, the number of actions, the number of players, and then, of course, the degree of the desired degree of privacy. In particular, if you think about a game like a random matching game where where you can hold fixed k, and gamma is of the order of 1 over n, you have that you can do approximate correlated equilibria for order 1 over square root n. Okay, so we are recovering. If you look back at the large games literature, and there's been a whole bunch of work on equilibria of like large double auctions, somehow they always find a 1 over square root n approximation of the efficient equilibrium. And well, here again we have 1 over square root n approximate equilibrium. So for better or worse, we're stuck with 1 over square root n, but we've gotten a little bit more. We managed to guarantee privacy. All right. This is good. Yeah.
Yeah, just alpha approximate mean additive error.
Alpha is additive, yes. It doesn't matter because the payoffs are normalized to 0, 1. So. All right. This is our main result. What I'd like to do now for the majority of the remainder of this talk is give you a sketch about why it's true, why we can't do much more in the sense that Ronen was asking, and why the results are tight. Okay? Oh, I'm sorry. I forgot to give you 2 other things. So far I only said that our mechanism is returns an approximate correlated equilibrium. I didn't guarantee that it was that it had the appropriate incentives. So in particular, we can show that you can optimally pick both the level of approximation in the correlated equilibrium and the level of privacy, so that you have order 1 over n to the 1/4 approximate incentives in terms of the game as a whole. So it's a order 1 to the 1 over n to the 1/4 ex post Nash for you to first truthfully report your type and then follow your suggested action. Finally, you might ask, what about welfare? We don't have a lot to say about welfare. On the other hand, There are results that suggest that for a large class of games, any correlated equilibrium achieves social welfare close to the socially optimal outcome, close in the sense of constant price of anarchy. These are a class of smooth. This class is called smooth games, and those results extend to approximate correlated equilibrium and therefore extend here as well. So if you're in one of those, if you're in a smooth game, then we're also got a finite price of we've got a constant price of anarchy, which means that the welfare of the solution of the equilibrium we select will always be a constant, at worst, a constant factor of the social welfare of the best Nash equilibrium. All right. Sorry, the best of the socially optimal outcome.
Yes, maybe I missed what you said. So you don't have any control on which correlated equilibrium.
We don't have any control on which correlated equilibrium, but any correlated equilibrium is better than the worst correlated equilibrium. The worst correlated equilibrium, and Tim's results tell us that the worst correlated equilibrium for classes of games is a constant fraction of the socially optimum, ergo, we're in that range. All right. This time, these are the results. Let me tell you a little bit about why it's true. There are people in this audience who could explain it slightly better than me, but let me try anyway. Our first ingredient is going to be regret minimization. The basic idea of regret minimization is, think about a setting where players are playing some stage game repeatedly. And instead of being concerned with their payoffs or their average discounted payoffs, at every point in time they're concerned about their regret. What is their regret? It's a counterfactual hindsight viewing measure that says, you know what, holding everything fixed, look at all the days in which I played action 1, and suppose I played action 3 instead. Or all the days where I played action 2, suppose I played action 4 instead. Or any such swap. Of all the days in which I played one action, I look at playing some other given action on all those days, holding everything fixed. This is, if that number is small for any possible swap in actions, we say that the agent has, that the player has low regret. And the theorem, which has been rediscovered a bunch of times, goes roughly like this. First, there exist algorithms that guarantee that a player will have low regret against any sequence of losses. All right. 2, if everybody is using such algorithms, so everybody has low regret, then the empirical distribution of past play approximates a correlated equilibrium. If you don't believe it, take it up with Ricky. All right. That part is reasonably off the shelf. Indeed, they proved it, so we didn't have much left to do, surprise. So what's left to do is to guarantee incentives, right? And of course, guarantee privacy as well, insofar as you care about that. The problem is that this doesn't tell you which correlated equilibrium you're going to pick of each game given the reports. So by itself, using this as a mechanism, you can't guarantee incentives. What we're going to do is, in every stage, instead of doing regret minimization on the true losses, we're going to add noise to the losses and do regret minimization on the noisy losses. Now, if you add enough noise, you can guarantee privacy. And as I stated earlier, there was one of the nice properties of privacy is that privacy composes nicely. So even if you run this regret minimization for a bunch of rounds, you're still going to retain privacy. Therefore, the recommended, since the whole sequence of losses will be private, it follows that the recommended action is also private. Now, since the recommended action is private, you can basically go ahead and convince yourself that you get incentives. So the main work we do, and what I'm going to sort of gloss over is or what I'm not going to provide the details, or just what I'm going to provide a sketch of, is how to add enough noise so that we can get everything to hang together. And the trade-off is that you need an insensitive game to make this possible. If you add too little noise, in the first place, you're not going to get any privacy. If you add too much noise, then you'll be taking too long to converge. So you'll be taking too long to get to be able to guarantee that that the underlying sequence of play has low regret. And as a result, you'll be if you need too many steps, then even though you've added a lot of noise each time, the privacy of the whole thing together will be it'll be unprivate. They need a counterpart to private. Public is not the right way. So
Mallesh?
yes.
In your initial setup, it
Yep.
seemed to me like there was one instance of a stage game that you wanted to play once.
Yes.
And it seems like we've moved to
Oh, sorry. Okay.
a setting where we're playing the stage game many times, and I missed why you were
No,
doing that.
sorry. I should have been more clear. The actual stage game gets played only once. How do I compute an equilibrium of the stage game? The mechanism asks everyone for their types. Once it has everyone's types, it has an underlying stage game. It simulates no regret play for a bunch of rounds internally within the mechanism. Now, as it keeps track of the simulation, it knows that the empirical distribution of play is an alpha approximate correlated equilibrium. It therefore, after it's done the simulated play enough times to be convinced it's gotten close enough, it then stops running the simulation, looks at the realized empirical distribution of play, and then picks out a joint thing. But the actual game gets played only once. This multiple rounds that I was talking about are only internally simulated by the mechanism itself. Okay, so I've taken this. So we're using this ingredient of regret minimization and low regret play. There it was when these papers were written, they were used as a notion of learning in a repeated game. Here we're not using it as a notion of learning. We're using it as an internal simulation for our mechanism to follow.
Is there a reason why we shouldn't try to think about a more direct? Like
The reason is proof theoretic purely.
based,
Sorry?
there's not a reason why we shouldn't think about a more direct, non-simulation based approach.
There is no reason other than I'll borrow a term from
You
your.
know how to do it.
I'll borrow a better sounding term. This proof theoretically necessary from Tim Roughgarden.
What?
Proof theoretically necessary. We need it for our proof. In other words, okay.
Your proof.
Our proof.
So subjective proof.
Let me put it alternately. We know that for any given game, the set of correlated equilibria are described by a linear program, right? We can think about the problem. As for every reported type by every player, for every sort of profile of reports of type, I need to pick one solution to each linear program in a way that is differentially private and has incentives. Okay, we don't know how to approach that directly. I can add the following. For a general class of linear programs, it isn't known how to do this directly. It isn't known whether this can be done directly. For the specific class that are defined by games, for the specific class of linear programs that are defined by some class of games, given everyone's reports, maybe. This is the only way we know how. All right. All right. So, cited Ricky, check. Mentioned linear program, check. All right. My PhD is not revoked yet. All right. All right. Just a little more detail. There exists a computation. there exists a computationally efficient algorithm that given any sequence of loss vectors over t rounds, you can guarantee 1 over square root t loss, as long as the vectors are bounded between 0 and 1. You can put this, now if you put this together along with the observation that the empirical distribution of low regret play is a correlated equilibrium, you therefore have a computationally efficient algorithm to compute correlated equilibria. You have a computationally efficient algorithm to compute the correlated equilibrium of a game, which is take everyone's utility vector, run the low regret algorithm for them, with the input loss being what everyone else is doing. And given the guarantees, you're guaranteed to get 1 over square root t approximation, holding the number of actions fixed. Therefore, you're going to get a better approximation of a correlated equilibria the more number of periods you internally simulate. I should be careful with the word play, of course, but here by play I mean the mechanism or the algorithm internally simulates. The main step is basically pointing out that low regret algorithms are robust to noise. So suppose you took, instead of the true loss vector, you gave everyone a loss vector that adds some amount of noise, random IID noise, to each action for each player. All right? And you ran the algorithm on the noisy regret, and you asked what is the loss with respect to true regret, with respect to the true losses. The theorem basically says that you're still going to end up with low noise. You're still going to end up with small regret. So instead of showing showing the low regret algorithm its true losses in every period, I can show it noisy losses in every period and still be guaranteed that what it does has low regret with respect to the true losses ex post. All right? And now this is a horse race between two things. If I add enough noise, every loss vector for every action is differentially private. So privacy composes nicely. So even if I do it a lot of times, I'm only going to degrade privacy by I'm going to degrade privacy by a bunch. Of course, the agent seeing his entire sequence of losses is an upper bound on how much he can learn from just seeing his recommended action. After all, if you give him his losses, he can compute his action. So it can't. So in particular, seeing your action can't give you any more information about other people's types than seeing the losses that your recommended action was computed from. And now the main thing is you just have to do a little bit of computation to convince yourself that when the game is insensitive, so when gamma is of the order of 1 over n, there's enough wiggle room to maintain privacy while accurately computing equilibrium. So you can add noise and run the algorithm enough times to get everything to work out. All right. Finally, we use an observation from McSherry and Talwar in 2003. They observed that if a mechanism is epsilon private, it is also epsilon approximately truthful. So the intuition for this should be reasonably clear. If it's private, that means that any one person's report does not change the outcome by very much, which also gives you approximate incentives. All right. Now let me conclude by just giving you two other results. The first is a tightness result. So we've shown that, roughly speaking, if you have a given sensitive or an insensitive game, then you can compute a 1 over square root and approximate equilibrium. We can show that you can't do much better any which way you slice it. So fixing a desired level of privacy, any mechanism that implements an alpha approximate correlated equilibrium in an n-player 2-action game with order 1 over n sensitive payoffs must satisfy alpha is at least 1 over square root n log n. So we're basically off by at most a log n factor. Isn't very much. All right. A talk in a CS department is not complete until I show you some reduction. So here is the reduction I'm going to use. There's a bunch of papers in privacy that ask the following question. Suppose I have a database where every entry in the database is a private bit. And every query just asks, tells me, okay, what is the sum of the bits 1, 7, and 8? Or what is the sum of the subset 6, 14, 23, and 29? Roughly speaking, it's the result of these papers says, give me any private mechanism which answers order n subset sum queries. So given a database of size n, it's answering order n subset sum queries. It must have error order of square root n. Okay? You basically can't get away with less noise when you answer all these order n subset sum queries simultaneously. If you had less noise, the person would be able to reconstruct enough of the database to violate privacy to begin with. The cute idea here comes from constructing a specific class of games that reduces the subset sum. So we're going to take an n-player game which has two kinds of players. Data players, each of whom have a private bit. They privately own a bit and their dominant action is either 0 or 1 depending on the bit. And then a bunch of query players. These query players are meant to be the queries over there. So their payoffs are only going to depend on the particular data players to whose subset sum they correspond. And their best responses are going to appropriately depend on the sum of the inputs of the sum of the private information of the data players. The query players themselves have no private information. All right? What we're basically going to show is that any approximate equilibrium of this game will involve answering subset sum queries, and therefore anything that's more exact than square root n can't be private. All right? There's a bunch of work. Most of the work here is because these are about answering sum queries, and here we need to make sure that even approximate equilibria don't allow you more flexibility. So just proving that any approximate equilibrium of the game rather than any exact equilibrium of the game requires answering subset sum is where all the work is, but it's not conducive to discuss right now. And then finally, you could ask the following question. You could ask, suppose I didn't want to just look at random matching games or games where the set of actions is fixed as the number of players grow large. Suppose you wanted to consider some class of games where the action space also grew. All right. The problem was in the old space we were adding independent private noise to each loss for each action, and since we were holding the number of actions fixed, that was fine. But now when we're letting the number of actions grow as well, we're going to have to add too much noise to guarantee joint differential privacy. On the other hand, luckily there's been a whole bunch of work, again from the privacy literature, that instead of just sort of naively adding independent noise to the losses, adds noise with more complicated methods. You have to do more analysis to make sure the thing is private, and you lose computational efficiency. So all we can guarantee is that there is some algorithm that is still going to retain all the flavor of the results that we wanted, which is approximate privacy, approximate incentives, approximate correlated equilibria. It's going to follow the same structure of the proof. It's just going to add noise more carefully than just IID draws according to some distribution. Okay? Those are the results we have. I just wanted to take a few minutes and tie it back into the literature There's, firstly, of course, more directly related to computer science, there's been a broad literature on studying how to privately release summaries of a database. We use it. My co-authors work on it, and indeed so does Ronen, so you can ask him if you're interested. More recently, there's been an attempt to try to figure out how to put together privacy and incentives. Not so much work in that area. There's there's the paper by Makshari and Talwar, and there's a related paper by Ronen and Violetta. Separately, there's been a lot of work in economics trying to understand incentives in large games. So trying to understand incentives in large games, the oldest paper I could find goes back to Roberts and Postlethwaite. I'm sure there's sort of less formal analysis going further back, but note that even this paper was written before the canonical order of the alphabet was pinned down. And this literature has sort of suggested that issues in small economies vanish in large economies, and the results come of two flavors. One set of results roughly suggests that you fix some mechanism, let the market grow large, and you get approximate incentives. So this is everything but the last paper. The last paper by Azevedo and Budish goes in the other direction. It says, you give me the setting you want, I can construct a mechanism that does the right thing and has approximate incentive properties, but they don't have any flavor of computational tractability. It's not a constructive note. It's not a constructive mechanism. It's just an existence theorem, realistically, in terms of applications. We, by contrast, if you like our setting, we have a constructive algorithm that you can use. The second literature, which is much smaller but is worth pointing out, is that you might say, well, you're getting this for free because you're assuming a large size, you're assuming a large game, and all I wanted to note is that there's been this old literature in large games that suggests that even though players might be small in terms of incentives or in terms of payoff, they might be informationally large. And therefore, taking care of incentives by itself is not giving us privacy for free. Indeed, it's the other way around. Taking care of privacy is giving us incentives for free.
Did you rule out that case by assuming this 1 over this
Sorry?
curve, this gamma of 1 over n?
Yes?
Like, it seems to me you ruled out the case that players can be informationally large.
No, I mean, in saying that gamma equals 1 over n, I have only ruled out that players are payoff large. Right? So, for instance, even though you don't...
By informationally large, you mean, suppose there's a distribution over types, right? Then if you knew my type, then you would know, maybe it's correlated, so you know everyone else's.
Well, I've got independence in my world, but think about it this way. Even if you don't know, even if I don't impact your payoff by very much, you might be able to figure out a lot about my type just from the 30-second leading decimal in your payoff might be 1 if my type is 1 and might be 0 if my type is 0. Right? In this sense, I have no payoff impact on you. The payoff impact on you is minimal. But the informational impact, what you learn about my type, could be very large in equilibrium.
Except that you have independence.
Even if you have independence, again, it could be the case that in a particular game, a very small but deterministic component of your utility is determined purely by my type. And therefore, even though types are independent, based on the payoff you observe for yourself, you learn a lot about my type. Again, the payoff you observe for yourself depends on my type. Because my action changes as a function of my type, and therefore your payoff changes as a function of my action, which is a function of my type. So even though I am payoff small, in terms of my action's impact on you, I could be informationally large. And this point was made by Levine and Pessendorfer. It's a paper in the AER that wasn't noticed very much. Well, it's in the AER, so I mean, how unnoticed could it be? On the other hand, both Eduardo and Eric and we both sort of ended up rediscovering it because we were in a coffee conversation with Preston McAfee, who was editor of the AER at the time, and he pointed us in this direction. So it has been observed that the two things are not equivalent: payoff size and informational size, and therefore you have to treat them differently. Taking care of incentives in our model is sort of easy intuitively because of the payoff size, but that doesn't guarantee privacy by itself. All right. Finally, open questions. Important to use the word open questions in a CS audience, so I'm told. Bottom of this is the hardest question of the lot. Goes back to Jason's question. Why are we doing all this complicated construction? Maybe there's some easier way to do it. We don't know. More formally, can we get subpolynomial dependence on K in polynomial time? Remember, we had only two options. One was a polynomial dependence on K, but therefore that was, of course, only that was only useful if the number of actions was growing slowly or holding constant. And secondly, I should have advertised this when we talked about the case of growing actions. We need to put restrictions on the type of on the size of the type space. Whether we can relax both of these assumptions and still get computational tractability, we don't know. We are basically reusing the median mechanism of Roth and Roughgarden. And more generally, in terms of mechanism design, what else can privacy say about? We can reuse this. The tools of privacy to just think about noisy monitoring in repeated games and say things there. We're not there yet, but we believe we have some insight. And similarly, we believe that this is a nice contribution to a world about mechanism design without transfers. We don't know how far we can push this. In particular, maybe there is some easy way, and this also goes back to the previous question of maybe there's a better equilibrium selection mechanism. Maybe there's an easy way to just say that you can take any general IC mechanism and make it incentive compatible and private just by adding noise. So maybe there's some reduction theorem that we can use to do this more generally rather than going through the constructions that we do. But we're not there yet, and we'd be happy if anyone has some future ideas. All right. That's all I've got. Thoughts, questions, comments, stunned silence?